A very warm welcome to OXXPUN, the Technic magazine with Wolfgang Rudolph. Hello and a warm welcome. I've chosen a theme today which is very difficult to make visible, because it is all around us, electricity. How we can measure power, electricity. And now we will start very simply. The professionals, engineers and technicians just don't listen. Some things have to be extracted that they seem wrong from professional view. But it is for the people who work with it, maybe measuring instruments, devices, maybe have to buy, that they at least understand what it is all about. Electricity, we know, comes out of the wall socket, out of such things that we have here. And naturally, I can measure them. I'll measure first the voltage, the electric voltage. I'll stick this thing in here. That is simply an adapter, so that I can measure the electricity. And then calculate the performance of it, because the performance to directly measure is not so trivial. And then I take here my measuring device. I'll just have to look how we do it. I'll put one in here and one in there. And what a surprise! 230.3 volt. That means we've paid our bills. Now I know the voltage. When I want to measure the electricity, then I have to naturally cut a line open, which is done with this adapter, and attach a user, and then measure with this. But so simple as it looks, it isn't. Just take these back out so that nothing happens. So, and take this out too. We have to do a little theory. Electrical alternating voltage means we have a sine wave voltage. There are many different forms. As the sine, it looks usually like I have here on the screen. So that is a pure sine. As we know, we have just seen 230 volt. That here is exactly 230 volt. And here is the 230 volt dyno. Just a moment, I'll show you with it the mouse. 230 volt, and that is a 230 volt line. As we can see, the sine wave goes much further over, and then down into negative area. What we measure, what a normal good measuring device does, we measure the effective value. Effective value, what is that? Simply said, when the volume that here would take this here and take this too, and put that in a rectangular formula as a model in clay, and don't change the mass, just form it into a rectangle. That would be the effective value. Good. We calculate with roots up to and so forth. Let's have a look at the next picture. Here we have drawn it. You can see 3 is our effective value, and 1, that is the top voltage. That means the maximum possible voltage by the maximum in sine is in the positive and negative wave, which comes by alternating current, because it changes its pole. And then there is naturally something else. The number 2, for example. The number 2 is the top of the top voltage, from the positive high to the negative high. It is natural. Double the height of the top voltage. That is the simple stuff, what comes out of the wall socket. But now I'll make it a bit complicated. Have a look at this, how we come to the effective value. At the top is our known sinus. In the middle, the green one I have there, took the negative half wave away. And at the bottom, I have took the negative half wave and put it in as positive. When the electricity is made equal, we have with one diode the middle graph, and when we have a full wave rectifier, a bridge. a full bridge. All the older ones know what a grey bridge is, and it looks like that's at the bottom. That means when I make out of this alternating current of 50 make direct current, it buzzes with 100 Hz, not 50 Hz. Now you see why that is still the effective value. Then comes what I've said, we have to between root 1, root 2, divide, and then we get our effective value, the top value. So, now it gets more complicated, because we only had the voltage. We want to measure performance. How much performance uses the fridge? How much performance does a machine use? A drill, a lathe, whatever. Performance is current equal to voltage. Current we haven't measured yet. We've drawn it up here though. And this line here, that is the voltage. That is the bottom UVT voltage to a certain time. Then we have here the green line. That is the current. One or other would probably ask, why is it weird postponed? By the highest voltage, the highest current should flow. Yes, if I have a real consumer, but they don't exist in the real world. We always have inductive and capacitive amount everywhere. Where we have electric coils, motors or whatever, our capacitors. And when it is only line capacity, and they ensure that electricity and voltage don't flow in phase, but postponed. And that is what we see here. And now it's clear, by a little resistance I can calculate easy, electricity times voltage finished. But when I have it here, then it's not so simple. I have to, every time here, UVT, also the current, EVT, have, and these two values have to multiply. And exactly at this place, where we don't have the maximum of the voltage, we are over the hill, and don't have the maximum of the electricity, but we have the product of this in the maximum. The blue line is the performance. As we can see, so simple to measure the performance it is not. I have to compensate this, and my electronics that do this have to do as well. I can't do 50 times a second 100 measuring values electricity and voltage take and quickly calculate. We need technique for this, technique devices. And if that is not complicated enough, we have in our houses a 3 voltage wire system, or 4 in some factories, a different thing. These 3 wires, L1, L2, L3, you have probably heard of, maybe by old electric ovens or other machines in factories and firms anywhere. What does that mean now? We transmit our electricity over 3 different wires, all sinus form, alternating current, but out of phase. Out of phase means for every line, because we have 3, we divide the full circle, it is 360 degrees, through 3, and then we have the maximum on every line move, so we have 120 degrees. And it looks like this. That is the creation. Maybe you can understand why 120 degrees moved. In the middle it should be a magnet, and the others are coils. And really it looks different, and the magnet turns. And you can see on the growth of the arrows in each coil, when the voltage is at its highest, and what comes out of it is something like this. We've got phase 1, phase 2, phase 3, move to 120 degrees each. Or it looks like our normal sinus, what we saw in our first picture. But we wanted to measure performance, and we know our devices, electricity and voltage push away, that we can't simply measure. And then it looks like this. Please don't give up. There are simple solutions for this. We have here at the top our voltage. That is the voltage of the single phase. Then we have here drawn the electricity, which is phase moved. Then we have the performance. It is here at the top, the black curve. Okay, in this case, it is not calculated yet. Something else comes to it. We have between the single phase and the single lines, L1 and L2, we have also a voltage. What we had up to now was the voltage to null. But we have between the single line also voltage between L1 and L2 and L1 and L3 and against N or whatever. That means, okay, I'll stop now, it's okay. I know it's very complicated. When we have the phase shift to the current and want to calculate the performance for all three phases, because you have a three-phase motor stood around, then with normal measuring instruments we can't get on. But I want to stop here now because it gets so complicated. With normal calculating it just won't work. We got to use Seisodimer camera, and I hated them in the school, or complicated calculating systems, and that means with I then you can do relative simple, but that means you have to learn it and have practice or use it every day. I only want to say that electricity, what comes out of this extension, we want to pull out, and the voltage. It all looks pretty simple, but the plug in and it is okay, but three-phase alternating current, it is exactly so. You can also work with the sockets, but the problem is, if you want to measure the performance, there we are stuck. No, not totally. A microprocessor, a very small processor, they can do a lot of tasks, a lot of measurements, and when they get the values for the voltage to a site A, and for this site A, the electricity, then they calculate very quickly the performance. And that combined for the three-phase, it tells all in all what I have used. And that are high specialized devices that do so much that the user and the reading of as humans made so simple as switching a switch. I have here from PCE N27P. It is a performance measuring device. I can put it directly into the electric branch. We turn it on and you can see a very clear display. It shows what it can do, and you can see I can measure up to 63 amps in a three-phase net. And in the menu I have the possibilities to call up different modes. For example, here VAR, VA, and the performance in kilowatt hours. And then we come back. It is from the usage very simple. What happens inside, very complex, and very quickly is the continually on three-phase voltage and measures blind power, apparent power calculates, and shows me, and is very simply connected. The connections are for every expert using this sketch here obvious. So you can see it. You can mix up. I have here the three lines. I have my N1. I have here the power supply with equal or alternating voltage. It is naturally cut off from the measuring coaxium. I have on the other side relay switches. You can see that here too there are the relays shown, the contacts, and there is in principle everything set, connected and finished. You can configure the software. You can also do special settings. 63 amps can the device maximum, and the measurements are naturally U, I, F and P. It is Modbus able, and the OLEC display is by direct lighting still good visible. If I hold it under our spots, you can still see it. Even in large halls where extreme lighting is needed, production halls, even there you can see it clearly. It's simply clamped onto a DIN rail, and that's all. And then you're able to monitor your machines. You should know that machines that have a defect at one time in the near future, that their performances change. Even the industry changes in time. And here you can read that something is going to happen soon. Possibly a maintenance work done earlier to avoid larger damage, for example, to avoid production losses. So once again, very compact, very small, simple to attach, and the usage of this N27P is simple, the programmable performance measuring device. The N43 from PCE is a power meter measuring device for 3-phase, and when I turn it on you can see shortly you become a display which tells you what it can do, what it is doing. For every phase an own display, the voltage, and we have down here the sum, VA and the sum in watt, and the frequency is naturally also shown. The device allows it to be set in different ways. That means you can configure here what we see. It is in different sides filed, which means different daily settings. That means when I have configured it, I can call it up here. And if you look down here to the left, it shows page. That are the different memories, you could say. Here it says error because there's no voltage attached. I would have to attach a wire to each of these connections now, but we haven't got any 3-phase electricity in the studio. And the device itself can 63 amp directly use. It is ISO 50001 compatible. I can keep in the rules of that. Then I am on the safe side, because nowadays there's a lot called for with the electric safety. What we also have here is an impulse out for the working power. That means I can attach a counter and then externally over 2 lines and let the counter me show like electricity clock, because it also gave an impulse out. Device does this too. All 3 phases cumulative naturally, and it would have a display far away for the power consumption. So as you can see, the display is lit up. It also has a RS485 interface and can be built into a Modbus system and built into a complicated process control. So connections, so that you can see them. Very simple, they are numbered, and here we have displayed onto which clamp what comes. The electrician doesn't need a handbook for this. Maybe a handbook for his purposes to set the different parameters that are possible to fit his machines, but not for the connections. And here we have a relay out, and so they are connected here. So a measuring device with which you can 3-phase simultaneously monitor what at the moment energetic in the machine happens. The ND20 from PCE can be directly built into a switchboard. On the front side it is IP67, Okay, okay, the reverse side is clear. You have to have the connections. It looks like this. Here's the description of the in and out connections. I can see straight away where L1, L2, L3 are, where N is connected and so forth. I have the possibility to see my measuring transducer, what I can connect, so that over the transducer I can measure grade flows. It is also shown here. It is no problem for a professional. Now I'll just switch it on. It takes a moment, then we can see ND1, ND20. As you can see, it has a large 3.5 inch LCD display with backlighting, very clear, unclean, very distinct. It shows here different values. To the left what performance there is, and to the right what is being measured. Here we see amps, here we see watts, now we see AR, now we see VR and PF. Okay, it has to show error because nothing is connected. The sum of all three lines, we get it all summed up shown. There is frequency. It must not have an extra supply. It gets its voltage out of the measured voltage. But when nothing is attached, I have here an extra power supply. It measures U, I, F, P, Q, S and PF. That means it covers everything that I can measure in a three-phase system. This device monitors and shows it all. And there's nothing left over there. There's nothing that I can't measure with this device. It is small, light and easy to install and serves to monitor your machine's park and to control, and you can be sure that all is okay when you just take a look at the display. There are things that make me happy. Technique is fun, I always say that when something bugs me. But that here I have a lot of happiness with. That is the ND30 from PCE, a 3-line power meter to build into a switchboard. I had one and it introduced itself. When you look at the display now it tells what it is called and so. There is the speciality. It said, look you have connected me to the internet. And I have got from the DHCP server, Imnet, and I've got myself an IP. And you can reach me over that. I'll write it here at the beginning, so log in. And it comes and reports in. And that is what it looks like on the PC. That means that you can monitor this device completely from afar, steer and partly program it. And that makes everything much simpler. Imagine you have many machines running and you have such devices attached to the switchboards. You can monitor them simply by going to the IP address. And you see everything what you can see here. So we said it before, you have here 3 lines. You can see here P1, P2, P3 and the sum, the performance in watt. North, what you can see is normal because there's nothing connected to it. Then also Q1, Q2, Q3 as well. And here we go over to the next side. It is here also the possibility to save different configurations, and there are also some saved before. I have also the possibility to install an old display, which is funny but not for me. And here's an absolute speciality to show harmonics of up to the 51st harmonic. We often have rubbish in our electric cables, and here we become the other values, sums and so forth. I can call up unbelievable many things which show me what is with me. Not me, but my machines in my company, what is happening. So let's go back. We have a device here that we can work with 20 to 60 volt voltage to be operated. That means it does not take the energy out of the wires that are being measured. I have attached a power adapter between it. So now we have a look at the screen. Here at the top we have the single times the pages. When I go over them, they are enlarged a little. Those are them that we switch through, but all here simultaneously, because here is enough space. Just go through here and you can see it is very clear, and I have really the possibility to monitor from a distance. And the measured values, also those. I have to scroll a bit here also. Those I can call up. It can also save measured values. So just turn that back off. Those are the harmonics again. They are here because nothing is connected. A bit of rubbish is hanging on. That is normal, probably the rubbish what we have here in our air. Here we have extreme values, minimum and maximum values on the single phase. It's all recorded here. I can look at it, but we don't have anything at the moment. Here's the Ethernet. It is normal like every device that is in a network. The possibilities to set it, I can put an admin password in it, user password. I have extra an FPI user that I can set. I can whatever, the FPI, turn off, give a permanent IP and so forth. That means of course with this device when I'm at home at the weekend and at the works, my machines are running from home, log in and have a look. And have the possibility to set alarms, to set limits, so when one is overstepped I can do something. Then it sends an alarm, that is also possible. I can set logical conditions and relay state as built-in. What it has to do when these logical conditions are fulfilled, should it turn on, turn off and so forth. Two different things. I could build in a siren to it, a flashing light or whatever. So let's go out. I can archive, and what I also have is Modbus and also a professional interface. Use what today is standard. Over this I can set many system controls. A device basically is to use for complete holiday, to test all the possibilities it has, and I turn it off and then turn it on and it runs. I have to connect naturally my electricity of what I want to monitor, but that is by all these devices simple. It always is described on the back. for everyone on site, so you don't have to look through thick user manuals. So you can directly see where L1 goes in and out, L2, L3. And up here I have the connections for the RS485 power interface. I can connect two thermal elements, can monitor then temperatures. I can link them logical too to set off an alarm whenever a temperature is over or understepped. So, and there is the A1, the A2 alarms. So a device with which you can do everything you want or what you can think of, and it is very important when you have valuable machines or devices so you can monitor them. What are they doing at the moment? Are they running good? Is there any idea that a problem is arising or such? And for this is the ND30 from PC Instruments is ideally suited. 4 power measuring meters for 3-phase alternating current from PCE. They're laid here nicely in a row. Let's start here. That is the PCE-N27P programmable device, which can directly measure 63 amps. I can put it directly to the DIN rail, as you can see, then connect it, and I don't have to do anything else. It measures U, I, F and P. I can also show the frequency. It can be used to monitor the ISO 50, 1001. It has an alarm relay. I can connect it to the Modbus interface, and as you can see, it has a very nice OLED display. What you can see from every angle, and when light shines on it, you can see it clearly. I can configure it with the software to my personal requirements. The next one in a row, that is the PCE-N30. It measures also up to 63 amps directly. It can U, I, F, P, Q, S and PF measure. And here we also have the possibility to attach it to a DIN rail. And then the installation into a switch box is very simple. It has an impulse out. I can connect it to an external service provider. I get an impulse that always switches further on when it wants to. It has a lit up LCD display that is also good readable. RS485 is obvious. Modbus interface is normal nowadays. So let's go to the next one. The PCE-ND20. The ND20 is thought of for the installation into a switch box. It is EP27 from the French Specialized, and it can U, I, F, P, Q, S and also PF show, and also measure. It detects incorrectly connected phases if you have, for example, swapped L2 and L3. It is operated with a separate power supply. I can put it into the plug on the wall, but I can also operate it with low voltage. The 3.5-inch display is lit up well. I can read it good. And that has also the RS485 Modbus interface. The last device, that is the ND30 net or PNet, that is what it is called. That is the device with the internet interface. I can attach it to my network. I can call it up in my network with a browser. It logs on with a user surface, and all these menus that I can call up and use, I can see on one display simultaneously. It has the possibility of 2 temperature sensors, PT100 to connect, so that I can measure temperature somewhere. It has alarm relays and then an analog out for such things. And also what I have to say is I can put in logical links. I can say when there the temperature is too high and there too low and the voltage is too high or the voltage is gone. All that I can logically connect. And when it happens, please start a siren. So here are no wishes open and no eye dry. So such things make fun. You can see the technical development is going into such daily things, and that what we humans can't afford to measure or determine is took over from such devices. And us as humans simply shown and simply to operate. And possibilities that I can simply change over to that what I want to see. So that is all for today. Well, I'll see what comes us next. I'll say goodbye and thanks that you watched. Bye.
Discover and order the latest measuring and test equipment now on www.pce-instruments.com.